Okay, you guys, isn't this fun? Oh, I love this stuff. So we got the alternating series estimation theorem. We did this, right? We plowed through this. We talked about um, estimating the error, which is plus or minus how far off the sum is if you stop at, say, the 7th term. Well, you evaluate the 8th term, and that is your error. It's the absolute value, of course, because error could be more than or less than. So here's what we did, just to reorient you. We did the sum on a calculator. Now, you're welcome to bust out, n equals 1, n equals 2, n equals 3, and let's see if my little pen thing is working. Oh dear, perhaps not. Let's see if I can grab a pen. Pen, please let me grab you. Okay. Oh, I can. So we said that if I go out to the 7th term in this case, so there's the 7th term, this is the error, right? 1 over 7 factorial in stopping at the 6th term, because the 6th term, the partial sum we found, and the error theorem says, well, if you want to stop at the 6th, then carry on to the 7th. Don't add them, just figure out the value of the 7th term. We did the same thing with this one. This time it just asked for the error. It didn't ask you to add anything up. So if you have the error, then we were stopping at the 15th term. So we evaluated the 16th term. Absolute value of the 16th term, not the 16th sum, but the 16th term, which happened to be 1/5, which relatively speaking in my brain, I would say that's not a huge, that's not a terrific error. You don't want to be that far off, I would think, so you may want to go beyond. And it's the nature of the series itself. All right, and then the very last one, we kind of blew through this one, I know. We said, I want to know where to stop. So this time it doesn't say, hey, stop at 15, you evaluate 16. This says my sum needs to be within 1/10,000th of the real sum. So what we did is we set up error, and notice its absolute value, because I don't care if it's positive or negative. No -1 in the world is going to care, because in absolute values it's going to pop out as a 1. So that's why this was just 1. Didn't care about that. What I did need to know is when this whole expression becomes smaller than 1/10,000th. And that's just algebra, right? So you guys are multiplying. Remember, you got to multiply in order to preserve the inequality. So top left to bottom right, top right to bottom left. You get an inequality, solve it, and we get n is around, or 4996. That's how many terms I need to add. So this is saying add that many terms, and you will be within 1/10,000th of the real sum. Now, of course, I can't have 0.5 of a term, correct? So there's no such thing as a half a term, because terms are integers, so we round it up. So if I go out to the 4,997th term, I'll be within 0.000, I don't remember, just 1/10,000th. Okay, so here comes the next. Find the number of terms necessary to approximate the sum of the series with an error less than 0.01. Now this is extremely like the one we just did. You guys can stop the recording and try this. So if you are listening to this, there's a little button, and you just stop the recording and try this. Okay, you guys, so wow, this is exciting. This is how I teach online. Okay, so we talked a little bit about. Okay, you guys, so hopefully you had a second to work on that. All right, so let's take a look at this. Find the number of terms. Now, if you were successful, you would have said 5 terms. And you might say to yourself, self, how did she do that? So we're going to do the same thing. It's the next term, which is -1 to the n plus 1. So next term plus 1 over n plus 1 to the 7th. I'm just kidding. I said that completely wrongly. N plus 1 to the 4th Okay, so we're just taking this guy, and I'm going to the next term. I need that if I want the error. So S minus Sn, I need the error. And remember, this is just a secret code for error. So I need that error to be less than tenths, hundredths, thousandths, 1 over 1,000. Okay, so we can simplify this. Now remember, the 1 doesn't matter. So I'm just going to say 1 over n plus 1 to the 4th less than 1 over 1,000. And then you can cross multiply in order. So you got 1,000, keep the less than sign, equals n plus 1 to the 4th. So then I'm fourth rooting everything. So take the fourth root and the fourth root. And that will release your n plus 1 because these cancel. And the fourth root of 10,000 is 5.623-ish. If I subtract 1, I get 4.623. N has to be greater than that. And that's why it's 5 terms. I can't have part of a term, right? We don't have parts of terms, they're integers. So your final answer is you got to go out to 5 terms, which is not bad, right? Just go out to 5 and you're within 1,000th of the real sum. If you stopped the recording, then you would have set up something like this. -1. Now remember, we're going to the next term. So n plus 1 is the next term. So n plus 1 plus 1, because that's what the, let me put parentheses around this, divided by n plus 1 to the 7th. This is a terrible pen. My error is going to be within that. So I could say error. On the AP, they don't do that. They say SN and, now I forgot. What the heck do they do? The error, and it's actually on the first page. So let me back up to the first page that we did. There it is. Ah, I went beyond it. So the AP is not going to just say the next term. They're going to write all this funky stuff. And remember that S means the real sum, Sn is where you're stopping, and it's going to be less than the term that was unused. So let's jump back here. So it's S minus Sn. So S minus Sn. They'll write that. You have to say, oh, that's error. How easy is that? It needs to be less than tenths, hundredths, thousandths, so 1 over 1,000. You solve that guy, and you should get n. And it, for me, it looked backwards. It said n is greater than 4.6. Ooh, 2,3. And you know my dyslexia, so if I wrote 2,3 and it's supposed to be 3,2, then you guys can do that. I can't remember if I did that weird thing today. So n has to be greater than that. Well, I can't be greater than a decimal unless I round it up. So you have to have at least 5 terms added together to be within 0.01 of the real sum. Okay, so here comes another one. Approximate the sum of the convergent series. Now, the catch with this one, and we really haven't talked about this yet, we haven't talked about, hey, what do I do if there's a factorial? I mean, you do n plus 1 factorial, and then how do I figure that out? I don't know how to solve for a factorial. So here's where you start. You say -1 to the n plus 1. Apologize for my writing. This is like ridiculous. To n plus 1 plus 1 factorial. That error has to be less than or equal to, and I think I keep leaving that. No, it has to be less than 1 over 1,000. Okay, so you work this stuff out. Obviously, the 1 doesn't matter. That's going to be 2n plus 3. But we've got a, 2n plus 3, but that's a factorial. And my job is to figure out when that's 1 over, within 1 over 1,000. So we cross multiply, you get 1,000 less than 2n plus 3 factorial. Well, how in the heck do I solve that? I have no idea how to solve a factorial. That's going to go on and on and on, right? It would be 2n plus 3, 2n plus 2, 2n plus 1, 2n, 2n minus 1. So factorials go down by 1. So I don't know how to solve that. But you have Mr. Calculator. Just throw that in for y1 and then go to your table. So you're looking, and this is a new computer that does not have the fabulous whatever it's called, calculator thing on it. So go to your table. You're going to have x, obviously, and y. And you're looking for where does where do the y values become smaller than 1 over 1,000. I'm just going to say 0.001. Okay, so obviously one term is not going to do it. When I went to 2 terms, so you got 1 term, 2 terms, 3 terms, 4 terms, 5 terms. Stop this anytime in case you're sticking it in your calculator. 1 term, I don't even remember what that was. I didn't even write that down. This is 0.0002. Of course, it's going to give it to you in scientific notation, but you guys know all about that because you're smarty pants. Okay, 0.0002. 3 is 2.8. Oh gosh, 2.8 times 10 to the something crazy power. Okay, that's for n equals 3. That's still too small. I'm so sorry, too big. So if I write that, let me write it out here. That's random. 2.8. I just had 2.8 times 10 to the negative 6. That's what that e means. So you're taking this decimal and marching it left. 1, 2, 3, 4, 5, 6. I got a decimal. All the bumps receive a 0. Remember, I'm trying to get it smaller than 1/10,000th. So I am going to say that is a mighty nice thing. Because I don't know if you can hear my cats. They are really hyper. I think they like math. That's what I've decided. They love to be up here. They love math, which is good. Math cats. All right. So that means this is term number 2. Term number 3 is small enough, right? So what am I going to go out to? What term should I go out to? So think about that. What term would be great fun? I would say term number 4, right? So all I have to do is go out to the 4th term. They don't care. Oh, maybe they want to approximate the sum. And you guys can do that. This means figure out the 4th term. So -1 to the 4th, 2 times 4 plus 1. And I need that to be less than, well, actually it doesn't matter. That's what I'm looking for. So 1 doesn't matter. 8 plus 1 is often 9. This is a factorial. Didn't write that down here. Figure that out. Oh my goodness. We already got that part, didn't we? I don't need to do that. They want the sum. And this goes back to your calculator. So we talked about how do you put that in your calculator. Depending on your calculator, what this will do is it'll give you a tiny error. So you don't need this. I forgot the question I was answering. Of course. So this is just calculator work. So you can review your notes for the calculator, sum of the series of the blah. Some of you have fancy dancy new flashy calculators that can do it all at once. Others of you have the fun older calculator. We have to do sum of the sequence, blah, blah, blah. Okay, here comes the last example for this part. Says approximate that sum to within 10, 100, 1,000, 5 thousandths of the real sum. So think about what you would do for that. How would you solve that? This one is solvable algebraically. So think about how you would do that. I want to give you some time to do that. We're about 12 minutes into the video, which is nice. So give you a little bit of time. I'm going to stop the recording, think about it, and then we'll come back to our regularly scheduled program. All right, we're back. So I'm hoping that you got 5 terms. You wind up with n has to be greater than 4.84. If you didn't get that, check with somebody in your group. Somebody had to get that, right? So you had to have 5 terms. You would set it up just briefly, 1 over n plus 3 to the third. And that I'm just using the formula. That has to be less than 5 over 1,000. Right? 5 thousandths, that's what this is. That's why in grade school you had to learn how to say them. Ooh, is that 5 thousandths? 5. Because we had to put them into fractions, notice. So all of math is your friend in this class. So when you solve this, you get this. Don't forget to multiply in order, preserve the inequality. You'll be having to take a cube root and subtract. So that means I'm not going to 4.84 terms, I need to go to 5 terms, which is exciting. So that's it. That's all for this. I gave you a worksheet, not a worksheet, I gave you a handout because one of the things that's new in the AP, it actually started last year, is when do you tell for an alternating series absolute versus, I don't remember what the other one's called. Hold up, let me grab the sheet. This is what you guys should have. Conditional convergence. So when can you say an alternating series absolutely converges? So what you have to do first of all is figure out, does it converge all by itself? So somehow, okay, here we go. All right. So if it just on its own converges, but if without the -1, let's say you look at that and without the -1, it's secretly a convergent geometric. So if it converges alternating and without the -1 it converges, then we say it's absolute convergence. That means it doesn't matter whether there's a plus, minus, or if you just ditch the minus to the end, the -1 to the end. If it converges both ways, we say that's absolute convergence. On the other hand, if you have the alternating series that diverges, like it just goes crazy, it diverges. But I guess I kind of said that backwards. This one is this is alternating. Oh gosh, that's hard to write. And this is without the -1. So without -1 to the n. The idea is the same. So if one converges and the one without converges, then we say absolute. If the so if the original converges, so that's my alternating, but without the -1 it diverges. So let's say it's, I don't know, a divergent geometric series, but with the -1 it converges, we say, well, that's conditional convergence. So without the -1 it would diverge. So here are a bunch of examples just so you can see what's going on. So this first one, and look at the tests that you use. So we usually use geometric, p-series, we use direct comparison, so don't forget about direct comparison. But those are the ones usually that we compare these to. So you look at this, notice it's alternating because of the -1. And if you actually work this out, it converges. Alternating series test, it is, those 3 conditions apply. Remember the 3 conditions for that were, I'm just checking it out so I don't make a mistake. You had to have positive terms, you had to have decreasing terms, and the limit had to be 0. So alternating series test, once again, was an has to be greater than 1. I'm sorry, greater than or equal to 0. My cat is now sitting on my pad. This is really way not cool. Move, Elliot. Okay. He's so cute. Okay, so it has to be greater than or equal to 0. The next term, wow, that was messed up. An plus 1 has to be less than or equal to. And I really should make sure that my less thans and less than or equal tos are good. I keep looking at the ratio test. We're going up to the ratio test. So I just want to make triple sure that I'm not lying. No lying shall occur. Yes, it's greater than or equal to, less than or equal to an, so decreasing. And I have to make sure that the limit is 0. So the limit AN is equal to 0. If all of those check out, if it's positive, decreasing, limit is 0, we say it converges by alternating series test. Anyway, so you've got this one is clearly alternating because of the negative. It's converging by the alternating series test, and without the negative, it's geometric. So we say this is absolute convergence. Check out the next one. This one is going to be conditional convergence, because if you check out the alternating series test, it works. All those three conditions apply. But you look at this, we could call that a P series, right? This is n to the first, or I could call it harmonic. Either way, I cannot spell. Either way, it's going to diverge. So we say that's conditional convergence. So you can see what you're looking at. So this guy, the next one, converges by alternating series, but it diverges if you do a direct comparison test. And honestly, I would do the limit comparison test too. I usually try that first, but if that fails, then you go back to direct. So this is just conditional. This guy's also conditional because it diverges with P, but it converges with alternating. And then this one, absolute, it's not the alternating series test. You can't use that because you don't have, why can you not use that? It's absolute, So, yeah, you can't use that. That's not something that, because if I put in 1, 2, 3, 4, 5, 6, and I multiply it, which I cannot see that on the screen, but you guys have good notes. This power is not going to cause the negative 1 to alternate. So this just reverts. It's just going to be 1. So this reverts to geometric, which you know is going to be 1 over 3 to the n. Well, actually, we could just rewrite that. 1 over 3 to the n. I could say 1 over 3 to the n. And if I really want to find the first term, you can yank out a 1/3, blah, blah. So that's clearly geometric. It clearly converges. So we would say it's absolute convergence. The only thing I used was geometric, so it would absolutely converge. So, and one thing I want to point out is deleting n terms. So if I start at 1 or 2 or 3, it does not change the convergence. People often ask that. So if this were n equals 2 or n equals 5, doesn't matter where you start, right? You got a thing and you're starting here at 5, it's still going to converge or diverge to whatever value it is, even if I don't include the 1. So question often asked, I'm going to stop the recording for just a second so you can turn your notes. We're going to look at the ratio and root test. All right, guys, so we have done a whole ton of tests, and you guys can fill this out. Usually at the beginning of class, we say, hey, all are on this list. You now have 9. 9. 9, 9, 9. Rhymes with fine. So you got 9 tests. You guys test. And the ratio test and the root test are kind of, well, the root test is kind of a dum-dum test. You'll like it. Ratio test says for exponents, and there was a problem that we did, I don't know, a couple days ago, and there was a factorial, and I said, hold off on that one because there is a test that we're going to use that deals with factorials. So here's the deal. And what you do for the ratio, okay, well, I hope you have time to look at this. If not, it's on YouTube and I will post it. And you can continue this on your own because there are no snow days in calculus. Oh yeah. All right. So does the ratio test. The reason for the ratio test is I've got something to a power. So I've got n over something to a power. Those are the ones. And notice it's not like n squared, right? If this is not 1 over n squared, it's not a p-series. So I cannot use to the n. This is an exponential. Compare the next term. I've got the absolute value of n plus 1. Gosh, this is so hard to write on. Crazy. 4 to the n plus 1 times 4 to the n over n. Okay, so here we go. 4 to the n plus 1. Well, these n's are gone, and I just get 1/4, right? I just have a 1 up here. So here's where I am. I've got 1 on the top, n plus 1, all over 4n. So what I'm doing, I want to know is the limit, and what gives me a clue is I've got exponentials. The minute I've got exponentials, I can't use p-series. Those are not exponentials. Those are, oh gosh, what are they called? I don't know. They're not exponentials. So I'm going to take the limit as n goes to infinity of the absolute value of the next term. Now the next term is going to be n plus 1 squared. 2 to the n plus 1 plus 1. I'm substituting n plus 1 in for all of the n's, because that's going to give me my next term. Whoa, that's so bad. Okay, let me try this. Do you not love smart boards? Don't you wish your homework were on smart boards? That would be such great fun. Okay, so this is over the original. So n squared, 2 to the, oh my gosh, n plus 1. I'm losing my mind. I'm losing what's left of my mind. And then I got 3 to the n. Remember, this is a big old complex fraction. like fix it. The pen's too fat. Let's try this one more time. One more time. So I'm going to do the next over the previous. Okay, so I've got n plus 1 squared. 2 to the n plus 1 over 3, and this is where I omitted this, 3 to the n plus 1. Okay, all of that is over the originals, n squared, 2 to the n plus 1, over 3 to the n. Bam. Now that looks ridiculous, right? You're just going to flip the second one, multiply. My kitty is about to do math. She is so smart. She knows calculus. Do you know that? Just the beginning. She just knows limits. And I taught her ABCs, which is helpful because you really can't communicate without it. I mean, in kitty cat language you can, but really it's harder otherwise. Okay, n plus 1 squared. 2. Now if I've got n plus 1, clearly that's going to be, this is a 2, to the n plus 2 over 3 to the n plus 1. Now most people just get in the habit of flipping and multiplying immediately. They just go, okay, this is 3 to the n over n squared. You're going to get tired of flipping, so no flipping. N squared 2 to the n plus 1. And by that I mean you just take this, you put the n plus 1 term on, and then flip this immediately and multiply, because why waste the time? So here I am, rock me like a hurricane. Oh dear, that's odd. Just move this little guy over. Okay. And now it's a matter of how do I simplify that? So I will go in fabulous green. 3 to the n plus 1 and 3 to the n. Those n's are going to cancel. This is just going to give me 1 on the top, and there's a 3 to the first left on the bottom. So there's a 3 on the bottom. N squared, there's nobody to cancel with. N plus 1 and n plus 2 is going to leave me a 2 on the top. N plus 1 squared and n squared, I can't do anything with that. There's nothing that it can simplify to because the bases are different. So I've got n plus 1, the quantity squared, times 1 all over 3 n squared. Now check this out. I'm taking the limit as n goes to infinity. Well, that's a pretty easy thing to do, right? These are quadratics. I don't really care what it is. The highest exponent is 2. So this is 1/3. So it converges by whatever test I'm on. What is this? That would be the ratio test. Look at that. You have to like listen to me. You could never ever write that ratio test. Gotta write the test. AP does care about that. Okay. Okay, you guys. So I'd like you to try this one. I'm going to stop the recording for just a second, obviously. Whoa, dude, what happened? Root test. Just see what you can do with this, and then I'll come back on and go through it with you. Okay, here we go. So, again, because it's n to the n, and because there's a factorial, big deal. You're going to take the limit as n approaches infinity of the absolute value of n plus 1 to the n plus 1, right? We're putting in n plus 1 in for everything, over n plus 1 factorial. Now I'm not going to make the complex fraction. I'm going to flip that original one and just say n to the n. I'm sorry, n factorial over n to the n. All right, and I need to know the value of that. Less than 1, it converges. Greater than 1, diverges. Equal to 1, no conclusion. Try something else. So n plus 1 factorial, this guy, I can expand it to n plus 1, n, and that's what I'm going to stop with. So n plus 1 times n factorial. And the reason I'm doing that is because I've got an n plus 1 on the top. That n is going to cancel with this, leaving just n plus 1 to the first on top. And then on the bottom, let's see, this n factorial happily cancels with that. So here's where I am. I've got the limit, n is going to infinity, of the absolute value of n plus 1 over, where am I? N to the n. Okay. Now you might say, well, how do I do that? That is not a polynomial over a polynomial. So I'm going to rewrite this in a snarky little way. I'm going to say, well, why can't I write that as, and this is n to the, let me see, I think I did something weird. Yeah, okay, so this is n to the n up here, n plus 1 to the n. It's the 1 that got killed. So this was n to the 1. The n to the 1 got wiped out. So n to the 1 and n to the 1. So I've got n plus 1. So let me get rid of this. This used to be n plus 1. This is so hard to write with. Okay. So this 1 canceled with that 1, and that's why you're left with n plus 1 to the n over just n factorial. Okay. So let that sink in. If you weren't sure what the heck I did, go back and listen to that one more time. Now this is my very favorite number in the world. Check this out. I got the limit. N is going to infinity of, I'm going to rewrite that as n plus 1 over n raised to the n. Right? I'm allowed to do that. And in fact, I'm going to share this n with both of the tops. So that's going to be the limit. N is going to infinity of 1 plus 1 over n raised to the nth power. And you should look at this and say with joy and glee, I know what that is. In fact, I am extremely happy. So if you look at that, you're going to say, whoa, this is the definition of E. And E is greater than 1. Therefore, this diverges by the ratio test. I can't write. Diverges by ratio test. Exciting. See all that E stuff that we did? E is just, I have got to get that tattooed somewhere. All right, check out the next one. I want to point out that I don't just have this. I've got a -1 that's flipping back and forth. So this one doesn't count. This is an alternating series. So don't just haul off and say, oh, cool, I have blah, blah. This is an alternating series. It goes back to what we did before. So I'm going to figure out, is it true that my terms are positive, decreasing, and the limit as n goes to infinity of my rule without the -1 goes to 0. If all of those are in place, we're good. So without the negative, I can check off, certainly the first one is definitely positive. Decreasing means that the square root of n plus 1, so that's the next term, over n plus 1 plus 1 has to be less than the original square root of n over n plus 1. So that's the same as saying the square root of n plus 1 over n plus 2 has to be less than the square root of n over n plus 1, right? Cross multiply. So I'm going to get n plus 1 times the square root of n plus 1 has to be less than, what am I doing? Let me think. Square root of n. So I'm going this direction. So square root of n, and then n plus 2. Okay. Now, this is not easy, and I don't think it's even possible without some exciting advanced math to figure this out. So what I would do is put this in your calculator. Put this in for y1, put this in for y2, and you're going to get functions. You're hoping that y1 is underneath y2. So let's say y1, and this is not the graph, but let's pretend that y1 looks like this, and y2 looks like this. So y1 is beneath y2. If that's true, then y1 is smaller, which is good. That means it's decreasing. And I know the limit, so this is limit as n goes to infinity of n to the 1/2. I'm just changing that square root over n plus 1. So n to the 1/2, notice this bottom has a larger exponent than this. That's going to 0, right? If it's bottom heavy, it goes to 0. We're good. So it's going to converge, not by the ratio test, but by the alternating series test. Okay, done with the ratio test. The root test, which is the last one we're talking about, I call it kind of the dum-dum test. I mean, it's really weird because you just like randomly make up this square root thing. So what it says, this is essentially the same as the ratio test. The rules are the same. So this is if I've got nth powers, so e to the 2n, n to the n, 2 to the n, and so something really simple to a power, maybe a ratio to a power. You can take the nth root of it, so that's what this is saying, the nth root of the absolute value of whatever the rule is, and check that out. So if the limit is less than 1, so just like the last one, it's going to converge. If it's greater than 1, it's going to diverge. And if it's equal to 1, no conclusion. Boo. So let's check this out. I think I only have 2 examples because it's really quite a simple thing. So this one, I look at this and I say, I am going to use the root test because this is something to a power. So I'm going to say the limit as n approaches infinity of the nth root of the absolute value of 2n to the, over n plus 1, all raised to the, move this out, to the nth power. Now here's why it's just kind of hokey, right? These cancel. It's like we just made something up. And do the limit again as n goes to infinity. So now I just have 2n over n plus 1. Whoa! Well, clearly that's just 2. So it is going to converge by the root test. Hokey, but fun. We just kind of made up a root and took it out. Okay? So try this example, see what you would do with this example, and then I will hook you up with the answer. Okay, and I just realized I made an error with this. If you look back at the top, what we said is if it's greater than 1, it diverges. I think I wrote converges. In fact, I know I did. So this last example, if you went, what, Miss Rubin, you are smoking something there. This is diverge. Okay, because it's greater than 1, 2 is greater than 1. Just like P series or like Geo, it's going to diverge. Okay, now you probably kind of, maybe, perhaps, weren't sure what to do with this one. I don't know. The limit, n is going to infinity of, now, I can take the nth root of this, but I also could say this is e to the 2n over n to the n raised to the 1 over n. So that's the same thing as taking the nth root, right? 1 over n is the nth, whoa, I wrote a 5, is the nth root of blah, whatever's underneath there. So 1 over n as a power. And the reason I wrote it like that is that I can multiply the powers. It makes it much easier. So I'm going to say the limit, n is going to infinity of e squared, right? Because 1 over n times n is just e squared, over n. Taking the limit of that, well, that is going to be, oh dear, what is that going to be? E to this, e squared over n, that's going to equal 0. And you would say 0 is less than 1. So because of that, it's going to converge by the root test. So now you guys can fill out these are all of the tests that we're using. So let me see if I can find the summary. You already started this. Strategy for success, organize your tests. Kind of rhymes. So you've already done a bunch of these because we assigned it before. Now you have the tools to finish this. There are no more tests. And so finish this, and then I will let you know what the homework is. And then next time we are moving into power series. So that's a whole nother topic. It goes into Taylor series and Maclaurin series, and you got to have your head on straight. You got to know your tests, and we will stop there. Okay? Have a fun day.